My name is Lisa Yang, and I'll be talking about the verification of quantum advantage from any non-local game. This is based on joint work with Yael Kalai, Alex Lombardi, and Vinod Vaikuntanathan. Quantum computing in theory and in practice has been a popular topic, especially in recent years. The primary draw of quantum computers is their potential to perform computations that efficient classical computers cannot. And the general question is, can quantum computers surpass the computational capabilities of efficient classical computers? In other words, do they have a quantum advantage when it comes to computing? And for what kinds of tasks? So this question has already been answered in theory, and the answer is yes. We believe that there are problems where quantum computers can give a significant speed up over the best known classical algorithms. For instance, Shor's quantum factoring algorithm is sub-exponentially faster than the best known classical algorithm. However, this is different from the question of whether we have quantum computers that surpass efficient classical computers in practice. In other words, do we have a quantum advantage in our current quantum devices? And the answer to this question is it's a work in progress. We have many companies now that are building their own quantum devices. And the question here is whether their devices are able to perform a computation that none of our efficient classical supercomputers can. And the main limitation of near-term quantum computers is they have a limited number of qubits. So whatever task we ask them to perform will have to be subject to this constraint. So towards having a demonstration of quantum advantage in our devices, we're on the search for a task where a near-term quantum computer can perform the task and where no classical supercomputer can. Now, there's already been several methods for trying to demonstrate quantum advantage in the literature. And the first is to just have the quantum computer implement a quantum algorithm for particular problems outside of the class P. For instance, Shor's factoring algorithm. And the issue with this idea is that basically the quantum circuits required are well beyond the size of the near-term quantum computers. Another approach that has already been implemented is to have a quantum computer sample the measurement outcomes of a random quantum circuit. Now, the issue with this is that it's actually unclear if the tasks are hard for classical computers to do. It's been a subject of some research work, and it's also inefficient to verify if the output is correct in certain cases. While it's unclear if this task is really a demonstration of quantum advantage, I wanted to mention that it does have potentially interesting applications. Work by Aronson and Hung, which is also part of this conference, shows that the random circuit sampling task can be used to generate certified randomness from quantum devices of the intermediate scale. However, that still leaves us with searching for a method to demonstrate quantum advantage. Now, we can get some insight by recognizing that trying to demonstrate quantum advantage actually has similarities with securely delegating computation. In delegation, we have a powerful computing device, which we call the prover, which performs a complex computation and tries to convince a weaker device, which we call the verifier, of its output. Now, the challenge is in designing a protocol where the prover is forced to actually perform the correct computation and give the correct output. So what we want is to have some kind of protocol between the weaker device and the powerful device that enables the weaker device to actually verify the correctness of the output of the powerful device. Now, in the setting of trying to have a demonstration of quantum advantage, we have a very similar setup where our quantum computing device is performing some task that supposedly is beyond the reach of any classical computer, yet somehow we want a classical device to be able to verify the correctness of its output. Now, when we talk about interactive protocols, we'll be talking about interactive arguments, which have soundness only against computation-bounded provers. And starting with the work of Berkeley et al. In 2018, we've actually had interactive protocols for verifying quantum advantage. In such protocols, a quantum prover can pass the verifier's checks, but a classical prover cannot. And so if a computing device is able to pass the checks, then we are convinced that it is performing some quantum operation. Now, briefly, the quantum advantage in these protocols comes from asking the prover to do an inherently non-reversible computation. And a main focus in the design of these protocols is to have them be NISQ-friendly, meaning we'd want to reduce the number of qubits required from the quantum prover as much as possible. And of course, we'd like to base the classical hardness of passing this protocol on well-studied assumptions. Now, if we actually go back in history, we have already for many decades had multi-prover protocols or non-local games for verifying quantum advantage. And an example of this is the celebrated CHSH game. In such a game, the verifier will interact with multiple provers. For simplicity here, I've drawn two. And what will happen is the verifier will send each prover a message, and then the provers will each respond with an answer, and the verifier will check some predicate on the queries and answers. Now, in such non-local games, if the provers are able to have correlations through sharing and entangled states, psi, then they are able to pass this protocol with some probability V star. And the guarantee is that any two classical provers cannot pass the verifier's check. The probability would be at most some V, which is strictly less than V star. And so if some set of provers is passing this game with probability V star, then we can be convinced that it is performing some kind of computation beyond the classical regime. However, the drawback of these games is that they rely on the assumption that the provers do not communicate, which is hard to actually enforce in practice. In this work, we show how to transform the latter into the former. Namely, we show how to transform any multi-prover protocol or non-local game into a single prover interactor protocol by using interaction and cryptography. More explicitly, our result is that any non-local game plus an encryption scheme with a sufficient homomorphism, which I'll describe shortly, can be used to construct a single prover protocol such that any efficient quantum prover in this protocol passes with probability, any efficient quantum prover in this protocol passes with probability at least V star, the value that entangled quantum provers can pass the non-local game, and any efficient classical prover passes with probability at most V, which is the maximum value that classical provers can pass the non-local game, which gives us a single prover protocol for demonstrating quantum advantage. Previous protocols for verifying quantum advantage were specific constructions, and one of our main contributions is that this is a very general framework that applies to any non-local game. Part of the take-home message of this talk is that the general transformation itself, we believe, is quite elegant and may have applications beyond giving protocols for quantum advantage. There are several open questions and recent follow-up work already, which I'll describe later on in the talk. So onto our transformation. So our transformation takes any non-local game. So for simplicity here, I've just taken a two-prover game. And the idea is to use encryption in order to enforce the spatial separation. So we can generically transform any such non-local game into an interactor protocol with a single prover, where the verifier samples the queries Q1 and Q2 as before, but it also samples the secret key for the encryption scheme. And in the first round of this protocol, it sends an encryption of the first query. And the prover here has the quantum states that the provers previously shared in the non-local game, and it homomorphically evaluates the first answer underneath the encryption. And then in the next round of interaction, the verifier sends the second query in the clear, and the prover simply evaluates the second answer. Now, at the end of this, the verifier decrypts A1 hats and gets back the first answer A1, and then it checks the same predicate as before. This transformation requires the encryption scheme to be homomorphic for the quantum circuit of the prover P1 from the non-local game, and to satisfy an auxiliary input property so that the circuit of the second prover P2 can be evaluated unencrypted. This property was previously considered already in BJ15 and is in particular satisfied by the quantum fully homomorphic encryption schemes of Mahadiev and of Berkeley. Now, the fact that the encryption only has to actually be homomorphic for the circuit of P1 raises the question of whether there are somewhat homomorphic encryption schemes that suffice to compile a particular game. And the hope is that such encryption schemes would be able to be much more efficient in the number of qubits. So in this transformation, so far we've shown that if there are entangled provers P1 and P2 that pass the non-local game with probability V star, then we have a single quantum prover that passes our transformed protocol with probability V star as well. Now, the verifier very righteously is asking whether we actually have any soundness in this protocol. And there are two kinds of soundness that we could consider. The first is whether quantum provers in this protocol pass with probability at most V star, meaning that they match the bounds for quantum provers in the non-local game. And the second question is whether classical provers pass with probability at most V. We affirmatively answered the second question in this work, and we raised the first question as an open question for future work, which I'll also discuss at the end. Now, to show the upper bound for classical provers, we consider any classical prover P tilde that passes our single prover protocol with probability V tilde, and we construct actually local provers P1 tilde, P2 tilde for the non-local game, which pass and show that they pass with probability V tilde. And briefly, this analysis involves constructing P1 tilde and P2 tilde by actually rewinding P tilde, which crucially relies on the fact that P tilde is a classical prover and not a quantum prover. And secondly, the crux in this argument is basically to show that P1 tilde and P2 tilde are indeed local provers. And this rests on showing that the answer A2 cannot actually depend on Q1 because Q1 is encrypted. And so basically the argument goes by showing that if A2 could actually depend on Q1, then this would break the semantic security of the encryption scheme. Now, since we know that in the non-local game, local provers can pass with probability at most V, we have that the V tilde here is at most V. And so basically in the transform protocol, we've actually preserved the gap between classical and quantum provers that we had in the non-local game. So the takeaway is any non-local game can actually be used to construct a candidate quantum advantage experiment that could be performed on a single quantum device. As a special case, we can apply our transformation to the CHSH game, which I'll briefly recall. So in the CHSH game, the verifier samples two independent random bits, X and Y, sends these to the two provers, which respond with 2 bits A and B, and the verifier simply checks if the XOR of A and B equals the product of X times Y. Now, it's known that if the two provers share an EPR pair, then there's a strategy that they can use to pass the verifier's check with probability 0.85. While if we have classical provers, they can only pass this game with probability 0.75. So we here have a gap essentially between the success probabilities of classical versus quantum provers, which we'd like to preserve in our transformation to a single prover protocol. Now we can apply our transformation as described before. One way to instantiate this transformation is to use the quantum fully homomorphic encryption of Mahadiev. And the resulting 4-on protocol would already improve upon aspects of the existing interactive protocols for quantum advantage. Namely, compared to Berkeley et al., our resulting protocol does not require the adaptive hardcore bit property, resulting in better efficiency. Compared to BKVV, our protocol would not require random oracles. And compared to KCVY, our protocol only requires 4 rounds instead of 6. However, we don't actually need the full power of quantum fully homomorphic encryption. If you recall in the CHSH game, the first prover P1 either measures in the standard basis or the Hadamard basis, depending on the value of its query. So all it's doing is it's performing a controlled Hadamard plus measurement. And so we actually only need the homomorphism for the controlled Hadamard. And so this leaves open the possibility that there are much more qubit efficient encryption schemes that would suffice for compiling the CHSH game into a quantum advantage protocol. And this is an open problem that I hope to see some progress on. So in summary, our results is that any non-local game plus an encryption scheme with the sufficient homomorphism gives a single prover protocol for quantum advantage. Namely, the gap between classical and quantum provers that you have in the non-local game is guaranteed to be preserved in the transformed single prover protocol. And in the full paper, we give the extension of this results for K-prover games and the analysis. And we also give a tighter analysis for handling games with super constant communication. The naive analysis requires the security of the encryption to be exponential in the communication, which works for constant size games like CHSH, but naively does not work for large games. And so we show a tighter analysis that works for some large games. Now, I wanted to mention some of the recent follow-up work and the open questions on our transformation. So the first is, can we utilize this framework, this transformation, to get a NISQ-friendly protocol? And the first main question is, can we improve the prover efficiency? The recent work of AMMW give a more efficient LWE-based protocol that builds upon our transformation for the CHSH game. However, for the CHSH game and in general, it remains open to see if we can improve the prover efficiency enough to be able to implement this on near-term devices. Now, one route to try to improve the prover efficiency is to construct more efficient encryption schemes, for instance, from number theoretic assumptions. In prior work to ours, KCVY actually used number theoretic assumptions in their quantum advantage protocols. So we wonder if similar or related techniques could be used for our transformation. Another question is whether sufficient encryption schemes can be constructed from general assumptions such as one-way functions. A second question in trying to streamline these protocols is if we can reduce the round complexity. The work of LMQW actually builds upon our transformation to construct a protocol with a different kind of quantum advantage functionality. They give a 3-round protocol based on our transformation that allows a quantum receiver to decode a message that a classical receiver cannot. The second main open question is whether our transformation is sound for quantum provers. Namely, how well can quantum provers do? We show a quantum prover can attain the success probability of entangled provers from the game, but can they do better? For the CHSH game, recent work by 2 groups showed that in the transformed protocol, quantum provers can only succeed with probability V star, meaning that they are as limited as the 2 quantum provers in the original non-local game. The question of how well quantum provers can do is actually very interesting for the question of whether we can obtain a delegation protocol for quantum computations by applying this transformation to appropriate MIP stars. If we apply this transformation to an MIP star and are able to upper bound the success probability of a quantum prover, then we would have an argument where a classical verifier could verify the corresponding complexity class. The recent work of Natarajan and Zhang mentioned above also apply our transformation to the MIP star of RUV and show the soundness of the resulting protocol against quantum provers, thus obtaining a delegation scheme for BQP. In general, it remains open whether our transformation is sound against quantum provers when compiling general games. But we already see that there's actually some interesting applications of this transformation. Now, the last and very general question is whether there are other general transformations from non-local games or MIP star, for instance, utilizing cryptography to useful single prover protocols. Our full paper is available on ePrint. And with that, I'll conclude my talk. Thank you for listening.